Okay, so we're going to get this session started. First of all, I want to welcome you all to today's Construction R&D Showcase. I'm Mike Matheson, Managing Director of Cognit.ca, and we'll be moderating today's discussion. The series is jointly presented by Cognit.ca and the Canadian Construction Association, and I really want to thank the CCA for all of their hard work and support in getting this session together for you today. The R&D showcases are part of a broader initiative that Cognit and the CCA have undertaken to help the construction industry more fully leverage the $14 billion of academic research that occur on campuses across the country every year. Another major element is the Construction R&D Hub, which can be found on the CCA's website. Using the hub, you can see recent construction industry related research and search for researchers, facilities, and IP that can help you address your company's next innovation challenge. I posted a link to it in the chat and would encourage you to check it out when you have a few minutes. Our format today will be a 10 to 15 minute presentation followed by a 10 to 15 minute Q&A. If you have questions for our presenter, please click the Q&A button at the bottom of the Zoom window and enter them in the box. I'll then read them out during the discussion portion of the program. For today's showcase, I'm delighted to welcome Dr. John Zellick, who will be presenting on automating visual inspection using AI. Dr. Zellick is an associate professor and co-director at the University of Waterloo and co-director of the Vision Image Processing Lab, or VIP Lab, at UWaterloo. He's also a professional engineer in Ontario. And with that, I'll turn it over to Dr. Zellick for his presentation.
Welcome, everybody. Thank you, Mike, for the introduction. What I'm talking about today is some work we've done the last few years on automating visual inspection. Most of the work has been geared on looking at automating inspection of infrastructure, in particular roads. So automating asset assessment doesn't necessarily replace workers, but allows them to do the work a lot smarter. In general, assessing assets is costly, requires a lot of data. And with people looking at the data, sometimes it's not objective, it's very subjective. And collecting this data and transforming it to produce an assessment of the asset provides insights and predictions in terms of over time, how will the asset degrade. So in particular, when we actually looked at looking at road quality assessment. And it's just interesting learning about how roads are assessed. Typically, large civil engineering companies are hired by cities and they drive around with expensive instrumented vehicles, collect a lot of data. A lot of the assessment of the stresses are determined by manual operators looking at screens. It takes a while to do that analysis and produce the reports. Typically, the data is collected in the spring, like April or May, and then they provide the cities the reports in September, October, not giving them a lot of time to actually do anything, since, especially here in Canada, winter is about to start in October, November. So in terms of road quality assessment in particular, collecting the data, we focused on looking at low-cost solutions as opposed to highly instrumented vehicles, trying to get all that information, for example, from a dash cam and a camera. If you take a look at most of the vehicles out there on the roadways right now, a lot of the safety features rely on cameras. So cameras are becoming more ubiquitous and prevalent in society, and making use of all that information, essentially crowdsourcing that information and processing that data in the cloud, can produce a map that outlines where the stresses are and predict how they degrade over time. And if you continually update that, that can give a city an indication of the state of their assets. Collecting data for roads, one can also look at other types of assets like sidewalks, trees, buildings, etc. So the process or the pipeline that we use, collect the data, we categorize the data, and first we separate the asset that we want to look at. So we focus in on roads. We compute the specifications, the dimensions, depth, and severity of the different distresses, and we build a map of labeled regions with road quality. So as I mentioned before, existing technology uses scanners, 3D scanners, and instrumented sensors, and right away cameras, and they require the essentially direct access to the roads. So what we're kind of spinning that completely around and providing a different way of doing things that is essentially we're not putting additional vehicles on the road. The vehicles are already on the road and are already instrumented, and we're making use of that information, whether they be residents of the city, um, fleets that are out there delivering parcels, or city vehicles. First step in terms of the pipeline is to isolate the asset. This shows one of our techniques of just isolating the roads, which is highlighted in the bottom picture. And this isn't a great example, but the neat thing about our particular approach is that there are shadows on the road, which sometimes, if you're processing image data, that can lead to problems. But our technique is robust enough that it ignores shadows, oil stains, still to detect the particular roads. And once we have the road identified, we focus on those regions of the image and we identify where the distresses are. Um, this actually is a road from Canada in southwestern Ontario. Notice that the red region in the middle image indicates where the faults are, and then we zoom in on that and actually delineate where the distresses are and identify them and bring them to the forefront. I'm not a civil engineer by trade. My background more, well, I'm a systems design engineer and electrical engineer. So it was interesting to learn that, especially for road distresses, there's a whole taxonomy of distresses. There are 22 different categories. However, there are 4 categories that are predominant, and they form 95% of all particular defects. And we focused on those particular defects for classifying what the distress was. And this shows categorizing one particular image and converting it from a perspective view to a top-down view. Um, Transverse cracks, the length, the severity. The severity was based on experts that define for us how you define the severity of a particular defect. Alligator crack, because it looks like an alligator. More examples of particular defects. And the one thing I wanted to plug here is that with a graduate student of mine and myself, we actually spun out a company called I for Infrastructure. We're actually trying to commercialize this technology, and we've had discussions with 6 to 8 municipalities of doing pilot tests of our initial technology. The interesting thing is about looking for the stresses, the technology is not only limited to applying it for infrastructure or road distresses. Recently, we've been talking to Bruce Power and the nuclear power industry, and actually one of my graduate students is working on a problem that's similar, but the pressure tubes in a nuclear power plant, they do the inspection of them, and the actual distresses are very similar to what we see on roads. So applying similar techniques can automate and remove the biases and actually speed up the process in terms of detecting these distresses in these pressure tubes. And this shows like the zirconium alloy tubes and roads, the parallels between the two, the defect type, the cause is different, whether wear and tear as opposed to absorbed deuterium, and the purpose of operation and detection. And there are parallels between the two. One of the techniques that we're using as opposed to standard computer vision is applying AI techniques or deep neural networks. And it's not really, some people play it up as being very simple, like a black box. And there have been great successes for doing various things in terms of recognizing different objects and detecting boundaries, detecting humans. However, there um, this shows two examples that, especially if we apply AI technology in the real world, that we want robustness, generalizability. For example, detecting a school bus as a snowplow doesn't really fly, and or for autonomous cars have to be robust. 99% accuracy level really doesn't cut it. It has to be almost close to 100%. I think in this particular accident, a person was walking their bicycle across the road, and the AI system had never seen that before. Either a person was on the bike, or the bike was by itself, or the person was by itself. So, I mean, these systems can be confused. Basically, they learn what you provide to them. And it's hard to provide all particular instances of what they may see. Just giving one example for computer vision, just playing up the odds in terms of the various camera poses, the lighting sources, the different textures that you can be seeing, the different materials that exist out there in the scene layout. There are 10 to the 39 different permutations, and there's no way you can provide a training system with that amount of data. And if we drew the analogy in terms of teaching a computer system on how to see different things and learn how to do things and automate the whole process, this is not how children learn. You show a few examples to a child, and it learns what to do with a particular object or a human on what to actually do. We don't have to provide every permutation. So that's where some of the research is going, trying to generalize and apply it to the real world. And tying it together, oh, this is a nice cartoon, a digression in a way. Now, look, all your babbling about the correlation not implying causality has obviously aroused the wrath of the gods. The reason I threw that in here is it draws parallel. Neural networks and AI are good at finding patterns. They're essentially pattern finders. And I mean, they are useful tools if used in the right way. We're working with a large manufacturing company now where we're looking for causality. If there is a defect, explain why that defect also happened, and using physical models of the road and how they deteriorate, and the data that we process and the knowledge that we get from that particular data, um, trying to find the causes and being proactive as opposed to reactive is very important. So some of the challenges that we're dealing in our research include the generalizability, explainability, not requiring a lot of data, applications, and we're trying to combine statistics, standard computer vision, and computational models with AI so we can have a more robust solution. The interesting thing that I presented to you in this brief presentation has focused on appearance-based methods, taking computer vision images and doing the analysis of that. But I mean, we can also have geometrical based information. What I mean, like depth images or LiDAR, and the vehicle of delivery of acquiring the data doesn't have to be a vehicle. It could be a drone, for example, in a construction site. And I do have one video to show at the end of this presentation that addresses that. And tying in with the construction, one other project that we have with the manufacturing company, we're using a similar technique to look and try to determine where bad welds exist, which I think are very applicable to the construction industry. So bear with me while I just load up this video and play it, and I'll explain it as we go. So the reason I find this really cool is this looks like a point cloud produced by a LiDAR, but what's being produced here is we have a single camera image, and the camera image like you would have on a smartphone, and all you're doing is taking that camera and moving it through the environment. And by movement, it's almost like having stereo vision through time. So we're able to recreate and determine where that camera is at any time and where all the obstacles are at the same time in 3D. So we can create the 3D environment. And why is that relevant? Why don't you want a sensor that emits energy out to the environment and it gets reflected back to get the depth? Or for example, for a drone, if you have a lighter payload, a camera, does not require an energy source. It's passive, so you can get all that information with less power and a lighter payload, especially on a construction site if you have a drone flying around to get the 3D layout of the environment. So I just wanted to throw that at the end, and I think my time is done. Mike, is that correct?
Almost to the minute. Thanks. So we're now going to transition over to the question and answer portion of this. Just a reminder that if you have a question for our presenter, please use the Q&A box at the bottom of the Zoom window. I'll try to get through as many of your questions in the remaining time as possible. Also, for folks that may have joined late, we'll be posting a few links in the chat window, both for the evaluation as well as for the CCA's construction R&D portal, which is a really neat way of finding research like what you heard about today, and in a variety of other topics that are construction related. So just sliding over to the questions. So you talked a little bit about the generalizability of the of algorithms, and that you are also able to that you're looking at road deterioration over time. How early in the deterioration process are you able to detect problems or potential problems?
Well, one of the things that a little slogan that we like to coin is that we like to see potholes before they're actual potholes. Potholes don't appear out of nowhere. It's actually pretty bad, the road, once you get a pothole. So this deterioration, you see this evolution over time. And the whole line of thinking of crowdsourcing and getting this information, that if we can acquire this information and process it on a regular basis, we can see that evolution over time. And knowing a little bit about the physical models of pavement, that the water is getting underneath and lifting the pavement and causing the cracks, that physical model, this is some of the stuff that we're currently exploring, how we can integrate actual physical models to explain that kind of causality in that evolution.
I mean, you've talked about tracking a particular asset over time. How, what's sort of the cost associated with that? That sounds like that's a high frequency, very high frequency, high touch kind of way of doing this. So can you talk about a little bit about the cost differential between this and one of the more, I think you called them heavily instrumented vehicles?
Well, a heavily instrumented vehicle, there's a lot of cost, but all the data is collected in one shot. And what we're talking about, especially for looking at road distresses, is that we're not adding extra vehicles on the roads. For example, a lot of fleets like UPS or FedEx, they already have cameras in the system, but the cameras are typically used for insurance purposes. For example, if there are false claims that the vehicle hit another vehicle, to have that data to back them up in legal cases. And we were talking with one fleet company about, they have this data and there is value of that data is already looking at the roads. And this is being collected 24/7 as these fleets actually operate. So there really isn't a cost. The only cost is uploading that data through to the internet, to the cloud, where the processing gets done. So essentially what we're proposing is a way of monitoring infrastructure with infrastructure that already exists on the roads today.
So could this sort of programmatic based data acquisition for identifying asset degradation be expanded to larger scale root causes, slope instability, improper drainage? And that one's from the audience.
Yes, it can. Right now, we're just looking on appearance and um, where the distresses are. But I mean, getting the 3D profile of the road and looking at drainage issues, or identifying water on the roads as we're collecting the data. We've actually thought about that, but we haven't explored that as of yet.
Which sort of brings me a little bit to the next question of where do you see the sort of the next steps for this research, more in terms of over the next number of years as you work it through?
Right now, a lot of the work, especially for road distresses, like I mentioned, we've been looking at purely camera image appearance based. We'd like to, and I've demonstrated at the video at the end that with single camera, we can recover the 3D. We don't need additional sensors. Having that geometrical information gives us other insights because sometimes there could be geometrical defects in a particular object that are not necessarily picked up by its appearance. Um, and one of the practical or pragmatic issues to address is actually being able to demonstrate that we can actually apply this in a large municipal setting, for example, and be able to do this on the fly as well. So that's more of a pragmatic concern as opposed to a research concern. Um, and extending this to other applications where drones are going to become more prevalent in society as well, and using them as a vehicle to collect data. And it'll be different types of data as well. I think if we're talking about municipalities, they talk about having 30 different assets that they track in a municipality. So um, it's roads are a big thing, but there are more assets than roads.
And then in terms of your conversations with the fleet operator or operators, is sharing that data something that they are open to, or is that a bit of a harder sell? How does that actually play out?
Well, we actually had conversations and made a business proposal to them. That's wearing my entrepreneurial hat, and basically sold them on the idea that there'd be another vertical revenue stream for them. And I'm not going to talk about numbers, and it made a lot of sense to them, and it became more of a practical issue. What was there sufficient detail in the images that they were collecting that we can actually detect the particular defects? To minimize costs, they were using cellular networks to upload all the images. We don't need all the images being uploaded in real time. So we were trying to work out scenarios, logistics in terms of, well, if the trucks are parked overnight and there's Wi-Fi available, using Wi-Fi and non cellular network to reduce costs in terms of upload. It doesn't make sense to upload all that data. And so issues like that, logistics.
And another question from the audience, but following on that theme, have is there is it would it be possible to make use of city-owned equipment, whether it's the buses or their existing fleets?
Yes, some of the discussions we've had with cities, we talked about using buses, garbage trucks. Garbage trucks traverse all the roads on a weekly basis. And one mayor suggested to us about possibly using police cars, but I think that might have legal implications as well.
I can imagine and then if we think about Canada's roads are in a variety of states of disrepair. And I think a study that the CCA did or was supported recently found, that 16% are considered poor or worse, while 23% are down to fair. Does this technology strike you as being useful at different, more useful or less useful at different stages of degradation, or is this really something that is equally applicable in sort of right across the board?
Well, the technology is more of a proactive technology as opposed to reactive. When the roads get in bad shape, it's going to cost a lot of money. But I mean, not all our roads are in that extreme state right now. So I lost my train of thought. So um, I, can you repeat the question, Mike?
So
Sorry.
yeah, it was just about whether you see this technology being used differentially depending on the current state of the assets, and you were starting to talk a little bit about that it's most effective as a preventative measure.
Yes, I was going to say something profound, but I can't recall what I was going to say. I think, um, well, now I recall what I was going to say. It was interesting the stat that you provided. The another stat from the Brookfield Institute, a think tank out of Washington in the U.S. These are U.S. numbers, but Canadian numbers closely parallel them. That every year, in terms of road maintenance and monitoring, there are $100 billion of inefficiencies every year in the U.S. So you can scale that up to 10. So what we're trying to address are these inefficiencies of monitoring. So being able to automate the process of, well, there's a longitudinal crack in the road. If we leave that, that will become a pothole over time. Perhaps we send out the crews to patch it right now, and being able to track and monitor. And it's difficult, just the logistics of monitoring where these distresses are, and money. Well, nobody wants their taxes to go up. So making use of your tax dollar in a more efficient way to maintain these assets, I guess that's what we're trying to get at.
And we're almost at time, but I have two related questions from the audience, so I'll sort of try to merge them into one. And that's about issues related to privacy from processing video data, and questions around whether municipalities or the private companies have a data sharing sort of fear and bias, and if so, how one might how you're overcoming that.
Well, in terms of privacy, we would want to blur out or remove that particular content, whether they're license plates, home addresses, or people's faces. And that technology exists to do that. So that's the quick and easy response to that particular question.
And are you finding sort of data sharing fears or biases, or have people been pretty open to the idea of doing that within the sort of the privacy guardrails that you just talked about?
I think once we state those privacy guardrails, the conversation becomes very comfortable.
That's great. And so that pretty much brings us to time. So first of all, I'd like to thank Dr. Zellick for his presentation. I know I found it extremely interesting, and I'm sure others did as well. I'd also like to thank the folks over at the CCA, Kenny, Mary, Nicole, and the rest of the team who have been so instrumental in pulling the session and the series together. Without them, this really would not have been possible. I'd also like to thank all of you for coming out today. I know all of your time is extremely precious, and really am extremely grateful that you found the time to fit this into your busy schedule. On that note, we are really focused on ensuring these sessions are as valuable for you as possible. To that end, we've created a short evaluation form that we'd really appreciate if you could fill out. I've pasted a link to it in the chat window, and in addition, it should open in your browser if you haven't already closed the Zoom tab. It should take you about a minute to fill out, and your honest feedback is absolutely critical to us as we try to continually improve these things going forward. Thanks again, and I really do hope everyone has a wonderful rest of the week. And with that, we will sign out, and thank you all for your time. Have a great rest of the day, everyone.